Hello again. This is Dr. H, and I am going to be doing another lesson on anatomy and physiology. Today's lesson, we are going to focus on autorhythmic action potentials and how autorhythmic action potentials are created. Now, what are autorhythmic action potentials? I think you guys should probably be asking yourself that first, right? Now, action potential tells us voltage. Action going to tell us that it's moving. So this is going to be the creation of current that is going to rush through the heart and go through the conduction pathways of the heart, reach into the myocardial cells throughout the atria and down into the ventricles. And when this current reaches those myocardial cells, it's going to cause those myocardial cells to contract. And when this current leaves those myocardial cells, it's going to cause them to relax. I just always think that it's important to review why we're looking at something in the first place. And that's why we care about autorhythmic action potentials, is because they create the heartbeat. What does autorhythmic tell us? It means us that it tells us that we have self-induced rhythm. All right, let's get to it. The heart is comprised of two different types of muscle cells. One are the autorhythmic cells, and the other one are the myocardial cells. The autorhythmic cells are the ones that create the heart rate, and the myocardial cells are the ones that create the stroke volume. You can look back at some of my previous YouTube videos to cover and review that material if you so choose. Now, these autorhythmic cells are called autorhythmic because they create their own action potentials. And they do that because they are leaky to different types of ions. Their membranes are actually leaky to different types of ions. So what we want to do here is we want to do a couple of things. One, I'm just going to draw a big, long, straight line. And this is just a quick representation of a cell membrane. We're not doing the phospholipid bilayer thing here, so I'm not showing you that there is this, polar, non-polar, polar end. I'm just going to do a nice flat line. And we're going to say that one side of this flat line has ECF, and the other side of this flat line has ICF. So this is all the fluid outside the cell. This is all the fluid inside the cell. And if we start thinking about the cells of the human body, hopefully you guys already have learned the fact that all cells of the human body have sodium potassium ATP pumps. Right? So we're going to have a pump. We'll just draw it in as a nice, big solid square here. And this is always moving. And we'll write in our name. I apologize here. So this is going to be the sodium potassium pump. They're found on every cell in the body. They require ATP for the function. They're working every microsecond of every single day. And what they're doing is they're moving sodium out, 3 sodium out to be more specific, but I'm not going to write that. And they're moving potassium in. Every single microsecond of every day. This should be review if you are watching this video. And that's going to increase the sodium concentration outside the cell, and it's going to increase the potassium concentration inside of the cell. So relative to each other, there's more sodium outside of the cell, and there's more potassium inside of the cell. And this is fantastic. This creates concentration gradients, which is the function of all pumps in the human body, is to create concentration gradients. Now, what else do we find in the cell membranes? We also find lots and lots of potassium leak channels. And a potassium leak channel is exactly what it is described as, right? This is just a channel that allows potassium to leak through it. And where is potassium going to try to move? From an area of high concentration to an area of low concentration. And where do we just say that the potassium concentration is the highest? It's the highest inside of the cell. Therefore, this potassium is going to leak out. And as it leaks out, what's going to happen to the membrane potential? what's going to happen to the total number of charges inside of the cell? Well, potassium has a positive charge, and as the positive charge leaves, then the inside of the cell becomes relatively more negative compared to the outside of the cell. Does that make sense? We lose the positive charges inside the cell as they leak out. Therefore, the inside of the cell becomes relatively more negative compared to the outside of the cell. And we can start to draw this as a graph, right? And that's what we're dealing with when we're dealing with action potential graphs. We're going to say what happens to the membrane potential over time. Everything in the body occurs really fast, so it's occurring in milliseconds. And then over here on the y-axis, we're going to say what is going on with the membrane potential. Membrane potential. Potential, that word right there tells us voltage. That's what potential means when we're dealing with in science. And everything in the body is happening in relatively small voltages, so we're working in millivolts over here. And if the outside of the cell has the same charge as the inside of the cell, this is subjective, I'm just trying to teach you a lesson. If the outside of the cell has the same charge as the inside of the cell, then what we'd say is the difference between the two sides is 0. But what do we now know? As potassium leaks out of the cell, what's going to happen to the inside of the cell relative to the outside of the cell? The inside of the cell is going to become relatively more negative. And there are going to be a lot more potassium leak channels than there are other types of leak channels in the cell. So potassium wins. Potassium leaks out, and continues to leak out until if there were only potassium leak channels, this would all go all the way down to negative 90 millivolts. And you're going to see that's not the case. Because the other types of leak channels that the autorhythmic cell has in it, well, it's also going to have some sodium leak channels. As do most of the cells of the human body, they're going to have a sodium leak channel. And where is sodium? Higher concentration outside the cell, right? There's more sodium outside of the cell than there is inside of the cell. And therefore, as these leak channels are leaky, it's going to allow sodium to start to leak into this cell, bringing positive charges with it, making the inside of the cell relatively more positive, which brings the resting membrane potential up just a little bit more. In autorhythmic cells, they also have other types of leaky channels. Okay, in fact, they have a leaky channel that allows calcium to pass through them. These are going to have a specific name that we're going to identify in just a minute, but let's just start out by saying there's some calcium leak channels. And whereas calcium higher concentration, calcium has a higher concentration outside of the cell relative to the inside of the cell. By the way, that's going to be created by a calcium pump. You guys will learn more about that in a later lecture. And therefore, calcium is going to be leaking into the cell through calcium leak channels. And what this does, it's going to bring this resting membrane potential up to its final value. In an autorhythmic cell, it's approximately negative 60 millivolts. And that is homeostasis, okay? That is created because of the net movement of potassium out of the cell, sodium into the cell, and calcium into the cell. Why do we remain relatively negative? Because there's more potassium leak channels than all the rest of these types of leak channels. There are other types of leak channels in an autorhythmic cell membrane. And these ones are going to be kind of novel, most likely, to y'all. Okay, there's another type of leak channel that has a name called funny channel. The funny channel is a sodium leak channel that has a gate on it. Okay, and this gate can open and close in a very transient manner. It can open and close very rapidly. It doesn't stay open, it doesn't stay closed. Okay, the funny channel is going to be what's called transient, which means it opens for short periods of time. And what do we know about transient things? Well, I kind of have hit this over the head here, but transient things are only there for a very short period of time. So this gate is going to open for a very short period of time and then close. Funny channels are sodium channels. Okay, funny channels are actually sodium channels. And what does that tell us about a funny channel is that they allow only sodium to pass through them in a transient manner. So that's going to allow sodium, which is normally high outside the cell. When this is open, then sodium is going to be able to leak into the cell through it. We're going to go back and refer to this calcium leak channel here now. Okay, the calcium leak channel that you see here is actually a transient calcium leak channel. It's also known as a T-type calcium channel. A T-type calcium channel. T-type meaning transient type calcium channel. And this one also has a gate, and if it's transient, that gate is not open all the time, it's not closed all the time. I'm going to change a color on my graph down below here, just so that I'm a little OCD about my colors. Because I made calcium leak channels up here a light blue, I want to keep it as such when we come back to our graph here. Awesome. Now, there is going to be another type of channel. And I think it's important to go through all these channels before we start looking at the graph, because you can't just, well, yeah, you can, but it's a lot more difficult to learn if you just start trying to memorize a graph. It's best to learn it by understanding the pieces of the puzzle. All right, so this one here is another gated channel, but this is going to be a voltage gated channel. And it's a very specific type of voltage gated channel. It's called a long-term or an L-type calcium channel. The stimulus for opening the L-type calcium channel is a voltage. Hence, it's a type of voltage gated channel. It's a type of voltage gated channel. That'll be important in just a minute. But when voltage stimulates the opening of the L-type calcium channel, what can pass through it? Calcium, right? Where is calcium highest? Outside of the cell. Therefore, calcium can move in. Easy peasy lemon squeezy. So far, hopefully not too bad. We're just going through the different pieces of the puzzle. Now, the last piece of the puzzle that we're going to see in this particular example, yes, there's one more. You guys got this. Stick with me. All right. Is another gated channel, and this is going to be another type of voltage gated channel. This is one that hopefully you've learned about before. This is going to be a voltage gated potassium channel. Okay, voltage-gated potassium channel is going to open due to the presence of voltage, of high voltage. And when it opens, well, potassium has a higher concentration inside the cell, so that potassium is going to flood out of the cell. That's going to end up driving the repolarization of this whole thing. So hopefully that's one you guys have seen before. So let's put all of this together on our autorhythmic action potential graph. All right. The first thing that we should think about, other than the setting of the resting membrane potential, the first thing that's actually going to happen is that when the cell down here is at resting membrane potential, it's going to be leaky to sodium because the funny channels are open. So what is the first channel that's open at resting membrane potential? The funny channels. Let's do that again. What is the first channel that's open at resting membrane potential? It's the funny channels. And as the funny channels are open, what ion can move where? Well, when funny channels are open, sodium gets to enter the cell, right? So we draw that in with a slight depolarization. As sodium enters, the inside of the cell becomes relatively more positive than it was before. But what do we know about transient? They're only open for a very short period of time, at which point they're going to close and something else takes over. Okay? When the funny channels close, that's when the transient calcium leak channels take over. And those calcium channels, the T-type calcium channels, they're going to take over all the way until this thing reaches threshold. What is threshold? Okay. I didn't do a very good job on my scaling on this graph, but that's okay. It's a learning experience. Doesn't need to be perfect. Negative 40 millivolts. If you look in your textbooks, you'll see that the threshold for autorhythmic cells is negative 40, but a lot of people haven't learned what the heck threshold even means. Well, let me tell you. Threshold is the energy required to open voltage-gated channels. So when threshold is met, a voltage-gated channel is going to open. Which voltage-gated channel is going to open here in the autorhythmic cell? Well, that is where those L-type calcium channels come into play. It's the L-type calcium channels that open at threshold. And what that's going to do is there's lots of these voltage-gated calcium channels on the cell membrane. So when they all open, it's going to cause a rush of current. It's going to cause a rush of calcium to enter the cell until it reaches about +5 to +10 millivolts. At which point, the L-type calcium channels are going to close. So calcium stops rushing into this cell. And what takes over? Well, it's going to be the voltage-gated potassium channels. Okay, at peak, those voltage-gated potassium channels fully open. They actually started to open down here because that's what threshold tells you, but they're very slow at opening. So they're not fully open until the peak. But at the peak, when these voltage-gated potassium channels are fully open, potassium is going to rush out of the cell, thus making the inside of the cell relatively more negative, and it's going to drive it back down. At threshold, those voltage-gated potassium channels start closing. A little bit of sodium starts leaking in, so we're going to get a little shoulder down here. But what's going to happen now? When the autorhythmic cell goes back down to resting membrane potential, the funny channels are going to open back up again. At which time, some sodium leaks into that cell. Then the funny channel closes. And once the funny channel closes, these T-type calcium channels open, so some calcium enters that cell until threshold. But what happens at threshold? Now the L-type calcium channels open, causing a rapid incline, depolarization step as calcium influx occurs. And then finally, that L-type calcium channel is going to close, and the voltage-gated potassium channel takes back over again, driving us back down towards resting membrane potential. Let's do this again. Now down at resting membrane potential, the funny channels are open, sodium enters the cell, but it's transient. It's a very short period of time, and then a transient calcium channel opens. You guys hopefully get the point. This is what creates the regular heart rate. Each time that your autorhythmic cells have enough leakiness that threshold is reached, an action potential burst is going to be created. And it's this action potential that now rushes through the conduction pathway of the heart. And as this action potential goes through the conduction pathway of the heart, it's going to reach the myocardial cells and it's going to cause the myocardial cells to contract. And when this action potential goes away, then current stops flooding through the conduction pathway and the myocardial cells are going to relax. Each time the action potential rushes through that heart, it causes contraction. When the action potential goes away, it causes relaxation. Now, when the action potential has gone away, it doesn't mean that it's not trying to make a new action potential. So this period underneath the curve right here is called the pacemaker potential. This is the potential for making a pace of the heart. This is the pacemaker potential down here. The action potential above the curve, the pacemaker potential down below the curve. Because I want you guys to start to think about something. What would happen if we reached threshold faster? What would happen if we, let me grab a different pencil here. What would happen if we reached threshold faster? What if we changed the slope of this pacemaker potential? Is the heart going to beat faster or is it going to beat slower? And hopefully you guys have answered, it's going to beat faster, right? We've reached threshold earlier, therefore an action potential will start here rather than here. And that reduces the time between action potentials and that increases the heart rate. So what's going to happen now if we make that less steep of a slope and we hit threshold later? Well, that slows the heart down, right? So we slow down the depolarization rate. What would happen if we hyperpolarized? Well, then we're even further from threshold, and that's going to make it so it takes even longer before it reaches threshold, really slowing the heart rate down. What y'all are going to find out is that's how the autonomic nervous system is going to function. The sympathetic nervous system, which increases the heart rate, is going to make it so we depolarize faster, versus the parasympathetic nervous system, which is going to slow down heart rate, is going to make it so that we reach threshold slower. Sympathetic nervous system, parasympathetic nervous system, you're going to have to learn the cellular mechanisms for how that works. The last thing that I would recommend everybody do, and I could help you guys do that here, is to write these steps down. Okay, I don't have a lot of room over here, but I do recommend that we write these steps down. Okay, so step 1. And actually, let's start with the step 0, because that's what a lot of the physiology textbooks have. Step 0 is going to be down here at resting membrane potential. Step 1 is going to be the opening of the funny channels. Step 2 is going to be the closing of the funny channels and the opening of the T-type. Step 3 is when we reach threshold, closing the T-type calcium channels and opening the L-type calcium channels. Step 4 is at the peak, where the L-type calcium channels close and the voltage-gated potassium channels open and come back down. So not too many steps going on here, and they just repeat themselves over and over. So step 0 is resting membrane potential. Step 1 is the funny channels open. And when the funny channels open, what ion can go where? This is going to cause sodium influx. Step 2, the funny channels need to close. They have to close. Each step of this process is important. If the funny channels don't close, or start to close at least, then we're going to increase the speed at which we reach threshold, which will come into play later. Funny channels have to close first. At least they start to close, right? And then what takes over here are the T-type calcium channels. And they're going to open, at which time we have calcium influx. It's moving into the cell, making it so we depolarize still. At step 3, well, the T-type calcium channels close. And the L-type calcium channels are reached, right? Because at this point, we're actually at, let's write that in, threshold. We're at threshold. Pretty darn important here, because at threshold, what opens? A voltage-gated channel. So here at 3, what type of voltage-gated channel opens? It's the L-type calcium channel. Opens. And when the L-type calcium channel opens, well, there's a lot of them, and this is going to cause a flood of calcium influx. A big rapid rush of calcium influx. Up here at 4 now, well, what's going to have to close? The L-type calcium channels close. And that stops calcium rushing into the cell. It stops the depolarization. And now we got to fix everything. Return it back to homeostasis. How do we do that? Voltage-gated potassium channels are the answers. Because when the voltage-gated potassium channels open, then we get a rush of potassium. Running out of ink. Potassium efflux. This is repolarization, right? This is a big step of repolarization as we return back to RMP. And down at the base, really at the beginning of 0, you can actually say now the voltage-gated potassium channels close. And that's going to reset the resting membrane potential at the base. All right. This is the autorhythmic action potential graph explained as a whole. Hopefully you found this helpful. Make sure you guys can identify all the different protein transporters found in the cell membrane and understand how they overlap with the graph that you all have to learn. Don't just memorize a graph. Understand what happens at each step and how this is going to be important to creating a heart rate, because that's what the autorhythmic cells are all about. All right, done here. Best of luck. Hopefully see you in the next video. Let's keep on learning. Humankind, be both.